All right, let's get started for today. A couple of announcements. Your project 3 is due on Friday. Next main event is midterm 1. That will be next week, Monday evening, 6 to 9 p.m. There will be 3 different rooms. Depending on your last name, you'll be in one of those 3 rooms. There is a preparation page. That preparation page has a lot of information about the exam. It covers what is covered by the exam. It has past exams. It also has a list of additional office hours which are held throughout this week, allowing you to catch me, any of the GSIs, to learn more about anything that you think you're not solid on yet that would be good to learn more about for the exam. There are also still regular office hours for Project 3. There is a practice midterm. What that means is that we posted a composition of past exam questions that you can solve for 1 point of extra credit on the actual exam if you submit it by Saturday night. The model is that you are to work on this for 3 hours on your own, or if you fully solve it more quickly, that's fine too, and then submit it. We encourage you to do this. We also encourage you to discuss with other students after you did so to learn more about how other students might solve the exam. We'll also post solutions to the practice midterm right after it's due. Any questions about logistics? All right, let's get started with the technical topics for today. And today we're going to start covering base nets, which we'll cover for the current and next 3 lectures, and then we'll see the 2 lectures after that, a special version of base nets called HMM. So we'll see a lot of base nets going forward. Let's take a step back quickly. So we're looking at probabilistic models. What are models? Models are some abstractions that we use to describe parts of the world. They're always simplifications. For one, we don't perfectly know how the world works, but even if you maybe knew how some part of the world works in great detail, you might not want to model in all that detail because it might computation be too expensive, or it might not matter for what you're doing, or at least the level of detail might be in the noise for what you're doing. So one thing to keep in mind here is that all models are wrong, but some are useful. A quote from George Box, who spent a lot of time modeling dynamical systems. For our specific scenario, what this will mean is that we'll consider certain variables in our models. Some variables in the real world will just not be considered at all. Then among the ones we consider, often in reality, they'll all interact in some ways, but we'll consider only a sparse set of interactions that seems most relevant to what we're doing, and hopefully that model that has only that sparse set of interactions is good enough for what we're trying to achieve. So what do we do with probabilistic models? We need to reason about unknown variables given evidence. That's probabilistic inference. An example could be explanatory reasoning or diagnostic reasoning, where given some symptoms, you try to recover the causes. It could also be prediction or causal reasoning, where you know what the world is like today, or some parts of the world are like today. You want to make predictions about what it will be like in the future. Weather prediction could be a good example. There are many situations. And then something we'll do once we have those all mastered is looking at value of information. And the idea there is that you can, with the right tools, compute ahead of time how valuable it is to you to find out a certain piece of information. For some things it's pretty straightforward. Somebody tells you the winning lottery numbers for next week. You can compute what that's worth to you, but there is a more general framework there that allows you to compute how much value there is to finding out certain variables, and then you can decide to either go measure them or not measure them depending on what the value is of other actions that you could take. Now, The main thing we're going to look at today is essentially understanding the simplifications we will be making. So let's start with independence. So what is independence? Two variables are independent if, and this is for two variables x and y, for all values x and y could take on, the joint probability of x and y is equal to the product of the marginal probability of x multiplied with the marginal probability of y. So this is saying that this joint distribution factors into simpler components. Two marginals, each only involving one variable. Another way to write this is shown over here. What is this saying? It's saying that for all x and y, the probability of encountering small x, given that you saw small y, is equal to just the probability of encountering small x. This is a consequence of the first equation. Remember what was this conditional here? The conditional for x given y is the probability of x comma y divided by the probability of y. Using the definition of independence up there, we get that's equal to, assuming x and y are independent, the product between the marginals divided by still py. Py cancels out, and we have that the conditional of x given y equals just the marginal for x. The second one might be easier to interpret than the first one. The second equation here is essentially saying, if you give me what y is, it doesn't change my distribution for x. It remains what it was before, just the marginal for x. Notation we'll use is this thing over here. It's like an orthogonal sign, but with two vertical bars. That we read as x is independent of y. Clearly this is symmetric. X independent of y, y independent of x, same thing. Because nothing in this equation here depends on whether x comes first or y comes first. Alright, so usually this will be a simplifying modeling assumption. Empirical joint distributions, the ones we observe in the real world, are pretty much never independent, but they might be close, in which case we might be happy to use the independence assumption to still model the phenomenon we care about in the real world. So let's look at an example here. Let's say we're worried about 4 random variables: weather, traffic, cavity, and toothache. So the question we're asking ourselves, would a somewhat reasonable model be able to assume some independencies between these variables? See some nods, right? So you might assume that weather and traffic are independent of cavity and toothache. Is that guaranteed to be true? It can depend, right? It's possible that you have a cavity, and if there was no traffic, you would have gotten to the dentist, your toothache would have disappeared, and so forth. There could be all kinds of dependencies that you might not immediately think of, but a reasonable model in many cases would be to say the first 2 are independent of the second 2. Now, mathematically, what does it look like to be independent? We saw the equations over here. That's the definition. So if we're given a joint distribution, we can actually verify whether there is independence or not. So we have a table here, 2 random variables, temperature and weather. Are they independent or not? Who thinks they're independent? Who thinks they're not independent? A lot of people think not. For example here, why do you think they're not independent? So the suggestion here was that the definition of independence that we show here in the slide is not satisfied. Now, I'm impressed that you're able to check that so quickly. We'll check that a little more slowly on the slide, but that's indeed what's going on. So how do we verify this as we break it down? So we have 2 marginals to compute. Marginal for temperature, marginal for weather. Once we computed those, we can now compute a new distribution, which is Pt times Pw. This is not necessarily equal to the original distribution. We don't know yet at this point of the computation. A lot of you already had a hunch that likely this will not be the same. probably mostly based on semantics of what temperature and weather are and how we've looked at it in the past. But now we can compute the product of the marginals, which gives us a new table where every entry here, for example, the 0.3 is the product of this entry here, hot, and this entry here for sun. We can now compare these two. Are all entries identical? If all entries are identical, then temperature and weather are independent random variables. If any of the entries are not identical, they're not independent random variables. So clearly some entries are not identical. In fact, all of them are not identical, but just one of them not being identical is enough to be able to claim that these are not independent random variables when you use this distribution. Now, had I presented you with this table over here, had I asked you, are temperature and weather independent according to that distribution, the answer would have been yes. Because for this distribution, it does factor into these two marginals exactly. Now, why would you care about independence? Here's the main reason. So let's say we consider a distribution over n random variables. Let's say they're coin flips. And each of them could come out heads or tails. If we have n random variables, we'll put them in one big joint distribution table. We have 2 to the n entries in that table. When n grows, that table will grow very quickly. At some point, if n gets very large, you won't be able to represent that distribution anymore. It'll be too large to keep in memory. And even long before that, probably you wouldn't want to because it would become really slow to work with such a big table. Now, equivalently, you can represent the same information by just having n marginals. Each of them 2 entries. So we have just 2 times n pieces of information to represent in the first representation, and 2 to the n in the second representation. And so by assuming independence, in this case the independence might actually be real, but in practice often it will be assumed, you have a much more compact representation to work with. Here we went from exponential in n to linear in n, which is a drastic reduction. It's the kind of reduction we're often after in computer science if you can, go from something exponential to something polynomial or even linear if you can. Now, the downside of independence, even though this is beautiful, is that effectively once you did this, your random variables don't interact anymore. Once you now observe one random variable, it's not giving you any information about another random variable. And so the whole idea of doing probabilistic reasoning is going to be pretty vacuous because everything is just independent in these representations. If you use this, and now there's no reasoning you can really do. The marginals already tell you the whole story. So we'll need something in between independence and having to deal with full joint distributions. And that's what we're after today. So the notion we'll need is conditional independence. So let's look at an example here. Consider the random variables toothache, cavity, and catch. So you could have a toothache or not. You could have a cavity or not. And then if a dentist robot goes into your mouth with a probe, that probe might catch into the cavity or it might not. Okay, so you can say if I have a cavity, the probability that the probe catches in it does not depend on whether I have a toothache, right? Because mechanically the way it works is the cavity is the thing that causes the probe to be caught, not the pain you're experiencing. So the way we can write this is that the probability of a catch for the probe, given we know there is a toothache and we know there is a cavity, is the same as the probability of a catch, given that we just know there is a cavity. Now, this is a lot like what we saw earlier. Earlier we saw independence means, x and y independent means px given y equals px. we're writing something and that would have to be true for all x and y, for the random variables x and y to be independent. We have something very similar going on here. The only difference is that in addition, we have a plus cavity sitting everywhere at the end on both sides here. If we got rid of the plus cavity, it would look just like what we had here for independence, but now we do have the plus cavity, and so we have that catch and toothache are independent given plus cavity. Right? Actually, they're not independent yet. It has to be true for all values, positive and negative, all combinations, but that's a very strong similarity here that you should keep in mind. Okay, the same independence holds if I don't have a cavity. The probability of a catch, given I have a toothache and no cavity, is equal to the probability of a catch given no cavity. Again, we can drop the toothache. It's independent of that given the other information. More generally, we say that catch is conditionally independent of toothache given cavity by this expression over here. And what that means is that this is saying for all values of catch, all values of toothache, all values of cavity, the above expression has to be true. If that's true, then we have conditional independence of the format I just described. Catch, conditionally independent of toothache given cavity. Okay, so there are some equivalent statements. Just like we had different ways of stating regular independence, we also had this version here. We could do something similar here. First thing we can do is swap the roles of x and y, so to say. In this case, that would be the roles of toothache and catch. Those are the ones that are conditionally independent given cavity. So we can swap their roles, and these two are equivalent. Then we can write it this way here, as the joint is equal to the product of the marginals. But keep in mind now, the joint and the marginals are actually not just joint and marginals. There's conditioning on cavity everywhere. Otherwise, that's the same as this equation up there. And since we have three different versions here, but each one of those three can be derived from either one of the other two. So you can just use any one of the three as a definition and then derive any of the other two from that. Okay, so that's conditional independence. The absolute or unconditional independence is pretty rare because often variables do interact, and in fact it's not that interesting because if everything's independent, as I mentioned, probabilistic inference becomes pretty useless. The marginals will be everything you get to deal with. So conditional independence will be our basic building block for everything we'll be doing in the next few lectures and how we'll be representing uncertainty. So formally, x is conditionally independent of y given z. And keep in mind this is actually symmetric in x and y. If and only if the joint between x and y given z is equal to the product of probability of x given z with the probability of y given z, and this has to be true for all values x, y, and z can take on. Equivalently, we have this expression over here, which you can prove from the preceding one. Something you might want to try on your own. We did it for absolute independence, prove the second one from the first one. You might want to try this on your own, see if you can derive it. Any questions about the definition of conditional independence? All right, so here's our notation for conditional independence. A lot like independence, but then we have the conditioning bar at the end, and we indicate which variable or variables, it could be more than one in some cases, we're conditioning on. So let's look at some examples. Let's consider three random variables: traffic, umbrella, and rain. And let's ask ourselves the question, are there any conditional independencies that might be true in a reasonable model about those three variables? Any thoughts? Over here.
Umbrella and
So the suggestion here was umbrella and raining might be independent of each other given traffic, right? That was not your suggestion, or you want to change your suggestion? Want to change your suggestion? Okay.
That traffic and umbrella are independent of raining.
Traffic? That's not the right semantic expression. The expression would be something, variable 1 is conditionally independent of variable 2 given variable 3.
Okay, traffic and umbrella are conditionally independent given raining.
Okay. So what do we have here? We have traffic and umbrella independent of each other given rain. Why might that be true? Well, let's think about what happens. The relationship between these variables could be that rain is something that just kind of happens on its own right. It's not influenced in any causal way by people carrying umbrellas, making it rain. That's not how it works. Same for traffic. Traffic conditions will not cause rain in any particular way. So rain just kind of happens or doesn't happen. Then depending on whether rain happens or not, people might bring out their umbrellas or they might not. And again, depending on just whether rain happens or not, there might be a lot of traffic or not, because rain tends to slow down traffic. And maybe more people go by car to protect themselves from the rain. Now, whether there's traffic or not, once you know that it's raining, knowing that somebody's carrying an umbrella is not telling you anything about whether there will be traffic or not, because you already know it's raining, and people carrying umbrellas has not any direct influence on traffic. On the other hand, if you were to try to claim, is umbrella independent of traffic without any conditioning, that's not really true, because if you see somebody carrying an umbrella, you might say, well, since they have an umbrella, likely it's raining, which likely means there is more traffic, and so this here would not be true, but now once you know the intermediary variable rain, they get decoupled, you have conditional independence. So the format here, in some sense, we'll get back to this later, is one where, in some sense, one variable kind of causes the other two to take on certain values. Oh, stay on. Okay. Okay, another example. Fire, smoke, and alarm. Any conditional independence relations between these variables that might exist? Any thoughts? Over there.
Can I ask a question about the last slide really quickly?
Of course, yeah.
So, would this same thing apply if instead of rain it wasn't raining? Would you say the same thing?
That's a great point. So I've explained the last example in terms of if there is rain, then that would influence traffic and it would influence people carrying umbrellas or not. When we look at these definitions here, it always says for all possible values these variables can take on, it has to be true. So for the conditional independence to be true between umbrella and traffic given rain, it has to be true that for each possible value rain can take on, once you know the value rain takes on, knowing something about umbrella or not is not telling you anything new about traffic or not. And similarly the other way around, knowing anything about traffic or not, once you know which value rain takes on, will not see anything new about umbrella or not.
So how is it conditional independence then? It sounds like it's like they're always independent.
So that's a great point. So the way it's conditional independence is, so I think the semantics you're getting at that is, I guess from an English point of view, perfectly fine, but not how it's mathematically defined, would be that conditional means it's conditioned on rain taking on plus rain, or conditioned on rain taking on negative rain, that we have independence, but it's conditioned on that specific value happening, right? And from an English point of view, that'd be a perfectly fine way to interpret this. what conditional independence means mathematically, and what this notation reflects, is that the independence between the two variables is true if that third variable has been observed, if you know the value of the third variable. And so that's where it comes in. It's conditional independence because you are able to condition on that variable because it's been observed. There is something called context-specific independence, and that refers to exactly what you are thinking about. Context-specific independence says these two variables are independent if that other variable takes on this particular value, and that would be called the context then. It's not something we'll look at closely in this class, but if you took a more extensive class on graphical models, you'd also run into context-specific independence. So that's the two names that are used, even though from an English point of view, you're perfectly right that it could have been a different choice if people had, but this is just what people picked.
Thank you.
Sure. So let's look at a second example, fire, smoke, and alarm, and let's assume the alarm can only trigger on smoke, not on heat. Any conditional independences that might be true here? Let's go with you. In the back, behind you. So fire and alarm are independent given smoke. What will be the rationale here? Well, you can imagine that the way things play out, first there might be fire or not. If there is fire, then there is likely to be smoke. Once there is smoke, the alarm might trigger. Now, once you know there is smoke, you already know everything there is to be known about whether the alarm will trigger or not. Whether that smoke was caused by a fire or not will not affect your analysis on whether the alarm will trigger. And so we have a different relation from before. The previous slide had one thing that could cause two things that were independent consequences. Here we have a chain in some sense, a causal chain where it starts from fire, goes to smoke, goes to alarm, and the middle variable makes the outer two independent of each other. Of course, you never know what really happens. Now, let's take a look at how we can use this for large probability distributions. We'll need to go back to the chain rule. This is the chain rule. It's saying that a joint distribution over any number of variables, in this case some arbitrary n, can be written as the marginal over the first one, conditional of the second one given the first one, conditional of the third one given the first two, and so forth until we get pxn given x1 through xn minus 1. Okay? So this gives us a trivial decomposition of distributions. Trivial meaning that this is always true. You don't need to make any assumptions for this to work out. Okay? So here's our distribution over three variables, traffic, rain, and umbrella. Applying the chain rule gives us the following equation. This is always true. Now the subtle reason why we're not really done here, why we don't say, well, we already got rid of our joint distribution, this is great, we solved our problem, is that actually the last one in this expansion is a table that's just as big as the original joint distribution because you have entries for every possible combination of values these variables can take on. So even though the chain rule might look appealing at first, as is, you'll need a little more than just a chain rule to reduce the size of the tables that you're working with. Sure, the very first tables will be small, but by the time you hit the last ones, they're still as big as what you started with. Now we can start looking at our conditional independence assumption. Our independence assumption was that, in our case, umbrella and traffic were independent of each other, given rain. So that means we can rewrite this, where we get rid of the traffic over here to get the new expression at the bottom. So we used conditional independence to simplify the chain rule expansion that we had, which is always applicable, to now have one that's specialized and only applicable under our conditional independence assumption, which was umbrella independent of traffic given rain. Now we actually don't have any table anymore that we need to keep track of that has all three variables in it. So we actually have a more compact representation than we started with. You can imagine as you have more variables, this effect will become even bigger as you start doing this. Okay? So Bayes nets, often also called graphical models, help us express these conditional independence assumptions in a more formal way. So let's start looking at that. So let's look at the Ghostbusters problem, again, the simplified version. At this point, the ghost can only be in one of two places, a top drawer or a bottom drawer. The sensor, so we can measure. The sensory measurement depends only on where the ghost is. We have two sensors, one for measuring the top, one for measuring the bottom. Now the top square is red, the bottom square is red, that's our current measurement, which means both are pretty bad, but in general the way it works out is that we have a distribution over where the ghost might be, top or bottom, and then we have a distribution for each sensor conditioned on where the ghost is, what it might read, red or not red, depending on whether the ghost is also there. So what we have here is something similar to the traffic domain, where effectively we have one cause, which is the location of the ghost, and two independent consequences once we know the joint cause. To write this out as follows, we have a full joint over the three variables that can be factored as probability for the ghost's location, and then two sensory measurement models that actually, as you expanded here, if you just apply the chain rule, you would have needed an extra t in the back for the last one, but because of the conditional independence assumption here, we assume the second sensory measurement is independent of the first one given where the ghost is. We can leave out the t in the back here, and we can expand this joint distribution with three variables into a product of distributions where none of them contain three variables. So they're all smaller tables. Now once we have those smaller tables, we can always re-expand it into a big table and recover the full joint distribution if we like to, but sometimes we might not need to for what we're interested in, and then we can fully avoid building that joint table while still really underneath having the equivalent information to a full joint table. Okay, so what's the big picture for Bayes nets? There are two problems with full joint distribution tables as our probabilistic models. Unless there are only very few variables, the joint is just way too big to represent explicitly. That's something we've been trying to do already, representing joint distributions. We want to avoid representing that full table. The other difficulty we'll run into in the future is that if you have a really big table with a lot of entries, you'll need a lot of data to estimate the values of those entries from empirical counts. And so once you start applying machine learning to learn the entries in your probability distribution table from data, you'll want the representation of your distribution that has a small number of entries. So two reasons here why we want to keep the number of entries that we need to provide either by hand or from data small. Okay. So Bayes nets are a technique for describing complex joint distributions using simple local distributions, just conditional probabilities that involve small number of variables. That's what makes them local and simple. A more proper name might be graphical models, but Bayes nets is maybe more often so used. We describe in a Bayes net how variables locally interact, and somehow then we also have a formalism for how these local interactions can be chained together into a global model, how all variables actually interact. So for the next 10 minutes, we'll be a little vague about how we go from these local interactions to the global model. We'll just build some intuition as to why local interactions might be meaningful to specify and might be a good starting point. So here's the first example. Let's say you're an insurance company and you're trying to model all kind of things that you care about when providing insurance, let's say for somebody insuring their car. You might care about their age, socioeconomic status, whether they're a good student or not, their risk aversion, their mileage, whether they have an extra car or not, the vehicle year, whether they have airbags, anti-lock, accidents that they might get into, and so forth. Now, some of these variables you can observe, some of them you cannot observe. But you can build a base net in this case that shows how all these variables interact. So in this case, it's saying, well, age might directly affect whether they're a good student or not, whether they are risk averse or not, whether they are senior trained or not, whether they have driving skill or not, and whether the medical costs would be high in case they get in an accident. Then you look at another one here, anti-theft might affect whether there's theft or not, and in turn it might itself be affected by socioeconomic status and risk aversion. So you break down this graph, essentially somebody put down all the variables they cared about and put down the direct interactions between those variables. There are simplifications there. In principle, you could say every variable interacts with every other variable, but the goal is to come up with a sparse set of interactions that's still pretty meaningful. Now in practice, what we'll be able to do is observe a few of those variables and then infer a distribution over the other variables. Now to do this with a distribution like this, which would contain roughly 20 variables, it'd be very expensive building a full join table and so forth. And we'll see more efficient ways to do this. Here's another example. Let's say you want to model how to diagnose your car when it breaks down. You can build a model like this. You could say, well, battery age will affect whether the battery is likely dead or not, which might be read off in the meter or not. Battery dead means it'll probably be completely flat, which can affect how the lights act, how the oil light behaves, the gas gauge, and so forth. And they might also be affected by other causes. And then there's the alternator and fan belt might affect that the battery is not charging, so the battery is actually not dead in and of itself, it's that it's not being charged, which also might affect whether the battery is flat, and so forth. Now, keep in mind, these don't need to be deterministic models. This is just saying a variable might affect another variable directly in a probabilistic way. That's what's being encoded here. That when the fan belt is broken, the alternator is broken, likely it wouldn't be charging. But you never know. Maybe just the heat cycles somehow is very hot and that partially recharge your battery or something. All kind of things could happen. Okay, so what's this notation here? Every variable that we care about is represented by a node. Okay. Some of these nodes could be observed, some of them not observed. Typically we'll shade the ones that are observed and keep transparent the ones that are not observed. Then the arcs are the interactions. It's very similar to what we had for CSPs, where we had a graph, nodes corresponded to variables, arcs corresponded to interactions. CSPs, the interactions were a little different. It was more a group of variables that together have to satisfy some constraint. Here it's certain variables might affect other variables in what you might think of for now as some causal process, but it actually doesn't have to be causal. Okay, so here's an example of a base net for the dental example. 3 variables, cavity, toothache, catch. Cavity is in some sense the first thing that we consider. Then it might influence whether there is toothache or not, it might influence whether there's a catch or not, but there's no direct edge between toothache and catch because of the way we're modeling things here, and we're saying that they're influenced by cavity directly, not by other consequences of cavity. Okay. So for now, let's assume these arrows mean direct causation in a probabilistic way. In general, they won't, but that's the easiest way to start building things up, and for a lot of base nets, this will be true, even if not for all. So let's do some examples. Coin flips. If we had n independent coins that we're flipping, what would the base net look like? Any thoughts? One suggestion is a tree. What's another suggestion here? Suggestion here is all independent since there are, and so as a consequence, no edges. So that's actually the correct answer. because there's no direct influence between them, it's a very simple base net, which essentially breaks down in n separate nodes and no connections. Okay, let's look at another one. Two variables here, rain and traffic. What kind of base net might we expect here? Over there?
We would see two nodes and an arrow going both ways.
So one suggestion is two nodes and an arrow going both ways. Over there?
Two nodes and an arrow going from rain to traffic.
Two nodes and arrow going from rain to traffic. So we have a couple of suggestions here. In fact, you can model this in various ways. One way to model it would be to just say they're independent, like what we did with coin flips. That would be a very crude model. Probably not the one we're after, but in principle we could. It'd still be a valid base net, just probably not the base net we want for all practical purposes in dealing with this domain. The base net that we'd likely want is something like this, where we have an arrow from rain to traffic because rain will influence whether there's traffic or not. Now, one suggestion was to also put an arrow back from traffic to rain to indicate that once you see traffic, it tells you something about rain. That's indeed true. When you see something about traffic, it'll tell you something about rain. In a base net, you don't encode dependencies in both directions. So you encode it one way, the way the influence runs, and by looking at it, you still know that when you run probabilistic inference in the future, when you see traffic, you'll know something about rain because you know that rain influenced whether there was traffic or not, and so just the arrow in one direction already encodes the fact that there is information flowing in either direction once you observe one variable. So the arrow doesn't denote flow of information that you can get, but it just encodes the influence from one variable onto another variable in what we for now think of as a causal pattern. Okay, so let's build a bigger model, and let's build a causal one. So bigger domain here. First variable, traffic. Okay, let's just put it down. Not much we can do if we don't know the other variables, but just putting it down somewhere where there is space on all sides. Next variable, it rains. Okay, natural choices make rain a parent of traffic. Next variable, whether there is low pressure or not. Well, the way weather works, this rain thing doesn't want to stick for some reason. There we go. Whether it, still not. Whether it is rain or not might be influenced by pressure conditions. That's just the way weather works out. So we might have low pressure over here, influencing rain. Also influencing traffic, maybe not. Maybe the influence of low pressure is mitigated through rain, and that way influencing whether there's traffic or not. Of course, these are choices. You can imagine everybody's depressed when there's low pressure, nobody gets in their car, stays in bed, you draw an extra arrow to traffic. Roof drips. Well, there needs to be some water on the roof for it to drip, so you can imagine that a reasonable model would say there is an arrow from rain to whether the roof is dripping. Another variable, whether there's a ball game or not. Well, what would that be influenced by? Ball games get canceled when there's too much rain. Oh, come on, Aaron. So, ball game might be a child of rain. Note that this is a negative influence. That's just as good. When there is rain, there's likely no ball game, or more likely no ball game. Ball game might affect whether there's traffic or not, if a lot of people are going to the ball game by car. So there might be an arrow this way. And then the last one, whether the dragon has a cavity or not. Well, that seems completely independent. Could be just sitting over here on its own. All right, question.
Can't D influence B?
Can D influence B? T.
Yeah.
Can T influence B? So traffic influence ball game? So what we're trying to draw here is a causal pattern. And the causal pattern we're looking at is that when there's a ball game, there's likely to be more traffic. It is true that when you see traffic, a lot of traffic, you might conclude that this might be caused by a ball game, but that's a conclusion you're drawing. That's not the underlying process underneath. And what we're drawing here is not how we might be able to conclude one thing from another, but we're drawing what the underlying process is that the random variables are generated accordingly to. Right, let's look at another example. This is the canonical example you see in pretty much any textbook about Bayes nets, the alarm network. What are the variables? We have burglary, so whether there's a burglary or not. We have whether an alarm goes off or not. We have whether your neighbor Mary calls, maybe because she saw or heard the alarm go off. Your neighbor John might call because John might have heard the alarm go off. And then there could be an earthquake, which maybe could trigger your alarm too, just because that might be how alarms work. So what would be the Bayes net here? Let's start drawing it. So earthquake would be one of the variables at the top. Oh, come on. So we start with earthquake. At the top. Burglary, we might put near the top too. Now, might it be that the burglary is caused by an earthquake because thieves take advantage of earthquake madness to go burgle? Might be. In the model that's used in most textbooks, they're considered independent events, so we'll do that here too. Then your alarm might go off based on somebody breaking in, which is the intended way for it to go off, but it also might be triggered by earthquake. Then your neighbor John might call, your neighbor Mary might call based on hearing the alarm, maybe wanting you to switch it off, or maybe wanting you to come and check it out and see if there is something going on at your home. Now, could you draw more arrows here? Could it be that maybe Mary will not call because she's already looking across the street and seeing John's already on the phone and says, well, John's probably already calling you, let me just not call anymore? Then if you think that's true, you draw an extra arrow between Mary and John. So there are lots of assumptions here, but this is the one you'll see in the textbook examples. All right, let's take a break here and let's start formalizing Bayes net semantics after the break. All right, let's restart. Any questions about what we've covered so far? Over there.
For this class, are we going to assume that Bayes nets are dynamic?
Great question. Coming up in exactly the next slide. The answer will be yes. Any other questions about what we've covered so far? Alright, so let's start unpacking the exact semantics of Bayes nets. So far I've been a little vague about what they are. We just built up some intuition that if there are lots of variables, maybe we can represent them in a graph and draw arrows for variables that directly influence each other. So let's formalize this. What is a Bayes net? To specify a Bayes net, you need to specify a set of nodes, one per random variable x. Over those nodes, you need to specify a directed acyclic graph. What does that mean? A directed acyclic graph is one where go through the graph and you find any cycles in the graph, then somewhere along the cycle you're not following the direction of the arrows. Another way to put it, there is no way to traverse a cycle in this graph while always following the direction of the arrows. This is important. There actually could be cycles if you ignore the direction of the arrows, just not once you also consider the direction of the arrows, then there is no cycles. A conditional distribution has to be specified for each node or correspondingly each random variable. And the conditional distribution that has to be specified is one that says, what is the conditional of that random variable given all its parent variables in the graph? So everything that's coming into that variable. It's a great way to describe a noisy causal process, right? Because you can set up your directed acyclic graph. The original cause is at the top, and it kind of, from causes, things influence their way down to consequences and so forth. It doesn't have to be a causal process that it encodes ultimately, but often those processes are easy to encode this way. So this is what we need to specify a basenet. In short, a directed acyclic graph and local conditional probabilities. Now, what do we get from that? It turns out that this implicitly encodes a full joint distribution. And the way it encodes it is by multiplying together all the conditional distributions that you just specified, one for each variable. Okay. So I'm just stating that here. We haven't proven this. I'm just stating to you in the previous slide what it means to specify a basenet formally, a directed acyclic graph plus conditional probabilities. I'm now stating that it turns out that then you can always recover a full joint distribution by multiplying these conditional probabilities together. So we now have a way to specify a full joint distribution over a large set of random variables through specifying a basenet. Okay? So here's an example. We have the dental example here, a basenet over the three variables, cavity, toothache, catch. We see the directed acyclic graph there. We have a full basenet specification. We'd also specify conditional distributions for each variable given its parents. So we need to specify a distribution for cavity. We need to specify a distribution for catch, given cavity, and a distribution for toothache, given cavity. Once you specify all three and the graph, you have your full basenet specified, and we're good to go. We can start computing things like, what's the probability of plus cavity plus catch minus toothache? Well, we just multiply the corresponding entries together of each of these conditional probability distributions, and that gives us the probability of this full instantiation. Okay? So in this case, we'd have this is equal to the probability of plus cavity, which we get from this guy's table, then probability of plus catch given plus cavity, which we get from this variables table, and then the last one is probability of negative toothache given plus cavity. All right, so that's procedurally how things work. Now let's show why this is true. So let's look at a full joint distribution over n variables, x1 through xn. N can be any number. Why we guarantee that if we draw a directed acyclic graph, specify conditional distributions for each node, and multiply those distributions together, that we get something that is a full joint distribution. Well, here's the derivation. We start from the chain rule. The chain rule says that any distribution can be factored this way. Okay. Now, let's apply our conditional independence assumptions that we need. So we're going to assume that xi is independent of all the variables that preceded in the ordering. So of all variables x1 through xi minus 1, except for its parents in the graph, given its parents. So that's what we just wrote here as our assumption. This is an assumption. This is not always true. We're assuming this. If we assume that, the original chain rule equation becomes this equation over here, which is exactly the equation we use to derive a full joint distribution from a Bayes net. So what this is saying is that effectively when we specify a directed acyclic graph, what we can think of what we did is that we specified some ordering of variables that's consistent with that directed acyclic graph. For that ordering of variables, we apply the chain rule, which by the way we can apply in n factorial different ways, but we apply for that an ordering consistent with our directed acyclic graph. Then we apply the assumption over here, which then tells us all we need is access to the conditional distributions that we have sitting in each of the variables, and that gives us the full joint distribution expression. So formally, what it means to specify a Bayes net when you provide this directed acyclic graph and a set of conditional distributions, you are saying that these assumptions are true. That for every variable xi, it's independent of all its preceding variables in the ordering, except for its parents, given its parents. And so, even though we've been talking about Bayes net as Bayes nets encoding causal processes and so forth, mathematically, really what they encode is this set of assumptions over here, independence of previous variables, except for the parent variables, given the parent variables. There's a question there.
So how does it work if one of the parent variables is not a preceding variable?
Then this derivation would not work. Exactly. And so for this derivation to work, you need to pick an ordering of your variables that's consistent with your directed acyclic graph. There will always be orders consistent with that. Now, if you specified a graph that's not a DAG, not a direct acyclic graph, then there will not be an ordering, because now you have a graph with directed cycles and this whole thing will not work out. And so this also explains to you why you need to pick a directed acyclic graph, because that's the only thing that guarantees you that you then have an ordering that you can use to then take these steps to derive formally what it means that you have specified a Bayes net. Alright, so we now formally know what it means to specify a Bayes net. It's specifying a set of conditional independence assumptions, as well as some numbers associated with these conditional distributions. Okay, so we can go back now to our Bayes net for coin flips. We can say, well, let's compute the joint probability of head, head, tail, head. Well, we know how to compute this now. Just multiply together the corresponding entries in this table, so it'll just be 1/2 times 1/2 times 1/2 times 1/2. Okay. Let's think about the formal definition here. We said when we specify a Bayes net, we assume a variable is independent of all its preceding variables given its parents, right? So what does that mean here? If we pick an ordering, let's say x1 through xn, we're essentially saying, well, for x1 we're saying nothing because it's the first one in the ordering. For x2 we're saying x2 is independent of x1 because x2 has no parents and x1 precedes it. Then for x3 we're saying x3 is independent of x1 and x2. For x4 we're saying it's independent of x1, x2, and x3, and so forth. Those are the specific assumptions that we're making. Now there are more independencies that we're not explicitly specifying that are just consequences of the ones we do specify. And we'll look at that a lot next lecture. Now here's another example. Rain and traffic. Here's the full Bayes net specification. What's the probability of plus rain and negative traffic? Well, all we need to do is grab the corresponding entries in each of the tables, multiply them together. Plus rain over here, then in the second table, rain and traffic both appear, so we need to look at plus rain, negative traffic, so the 1/4 entry here, and so we have 1/4 times 1/4. Alright, here's the classical example for basenets. Burglary, earthquake, alarm, John calls, Mary calls. What does the basenet fully specified look like here? We're just looking at the DAG. We need to specify tables. So this is what the tables look like. Why does alarm have the biggest table? Because alarm has the most parents. Generally, you'll see what happens is the size of the table is based on the number of variables that participate in it. And so something to keep in mind here is as you specify your basenets, be careful about giving any variable too many parents. Because if you give one variable, all other variables as a parent, now you're back to the size of the full joint distribution. In general, the smaller the parent sets, the smaller your tables will be, the more compact your basenet. Of course, you might be making approximations. So that's the basenet for the alarm network. Now, let's look at traffic again, and let's build the full joint table. So this is what we're specified initially. And from this, we can build a full joint table. Right? And each entry in that table is just a product of entries that we have in the original tables. Now I'm going to play a little trick on you. Play close attention. Look at these numbers here. 3166, okay, out of 16 for the full joint table. Designing a new basenet where I'm reversing causality, so to say. I'm saying that I'm going to draw the arrow from traffic to rain. These are the tables I'm specifying. From that, I can compute the full joint table again. We know how to do that. And it's again 3166. So what just happened here? We have two different basenets. The causal one, which might make most sense to us, and the reverse one, both have the same joint distribution. So they both encode the same probability distribution. If we do inference in either one of those basenets, use either one of those basenets for any purposes, we'll draw the same conclusions. It's just that we started from something different. And so what's interesting here is that different basenets can lead to the same joint distribution. In fact, this will be true anytime you just have two variables like we have here. You can draw the arrow in either direction for any distribution and still end up with that distribution, no matter what the underlying pattern is. Now, some of you might argue, I like the first basenet better, because I understand better the pattern of rain causing traffic in some sense. And that might be true. And what that means is that when you're specifying this first one here, let's go back to it, you might have an easier time coming up with these numbers. You might say, well, probability of rain, 1/4, seems reasonable. Then probability of traffic given rain, well, I think traffic will increase, decrease based on whether there is rain or not, and I can fill in some numbers here. And that might be a reasonable thing for you to do, reasonable thing for you to model. Now the other way around, it might just be much harder in practice to come up with these numbers. Especially for the second table here, you essentially need to infer what the likelihood is of rain given that there is traffic. That's not a pattern that corresponds to with how the world functions. The conditional distribution still exists, but it might be much harder to elicit. And so the reason you'd prefer the first one over the second one is not because the first one can capture a joint distribution that the second one cannot capture in this case. It's because the first one allows you to specify this joint distribution in a much more convenient way than the second one allows you to. So, general, you can ask yourself the question, well, how does causality interplay with specifying basenets? So, Here's how we think about it. When basenets reflect true causal patterns, it's often simpler to specify the basenet. Many of the nodes will have fewer parents. Often it's easier to think about how these parents influence that node, and easier to get expert advice, or if you're an expert yourself, use your own intuition to fill in the numbers into those tables. The simpler will matter computationally, because less parents is good. This will matter just in terms of how to specify the numbers. Now, they don't need to be causal. There's nothing in the definition of baseness that says a basenet has to specify a causal pattern. All it says is that if you're going to specify a joint distribution through a basenet, what you are assuming is that a variable is independent of all its preceding variables given its parents. That's your assumption, right? There's nothing in the formal mathematical semantics of basenets that say you are assuming causality. Now, when you consider traffic and drips, something completely different comes up. You want to draw a basenet that just considers the variables traffic and drips. We know that we had one before where there was rain that could cause both, but now rain is not in our basenet. How are we going to draw the arrow now? There isn't even a way to draw it in any causal way, right? It's arbitrary which way you're going to draw it. We know that they influence each other through this variable that we don't have available in our basenet, and so we have to draw a direct connection here. This also suggests that often you might want to pull in variables into your distribution, like in case, even if you're only interested in traffic and drips, you might still want to have the rain variable in your basenet to get a model that is easier to work with to capture what's happening in the real world. And often that's how you might end up with hidden variables that we talked about in last lecture when you run inference by enumeration. You have these hidden variables, variables that just are sitting there, don't appear in your query, but are somehow part of your joint distribution. And this is why they will often be part of your joint distribution, because the basenet you specify, including those variables, will be much easier to specify than one that excludes them. Okay, so keep in mind what the arrows really mean is this thing over here. And really, what you should think of is the lack of arrows that means something. As you work through your ordering of nodes, making no assumptions about your variables, no conditional independence assumption would mean that the second variable gets an arrow from the first one, the third one gets an arrow from the first and the second one, and every time you add a new variable, it gets an arrow from all the preceding ones. That means you have no conditional independence assumptions. And it's once you start leaving arrows out that you're making conditional independence assumptions. You're saying, not drawing this arrow from this preceding variable, so I'm assuming it's independent from that preceding variable given its parents. All right, so where does that put us in terms of basenets? So at this point, we have built up an understanding of what it means to specify a basenet, what assumptions we're making, and how it encodes a full joint distribution. Next, what we're going to look at is what other conditional independencies are true. So we'll see that assuming a variable is independent of its preceding variables given its parents, that set of assumptions will apply other assumptions that we're not explicitly making, but that will always follow from those initial ones. We'll look at what those are next lecture. It'll be really important to understand your implied conditional independencies when you're modeling things. The lecture after that, we'll start looking at how to answer probabilistic inference queries with basenets without having to first build the full joint distribution and then running inference by enumeration, because then we'd be back to a very expensive procedure. We're going to look at how to directly compute with things we specify in the basenet and still answer probabilistic inference queries. And from there, we'll then start looking at cases where actually even that becomes impractical and start using approximate methods. All right, that's it for today.